Morning everybody. Today we're going to start having a look at moments, which possibly might not mean an awful lot to you right now. If you do physics, then you may have come across this already. So what we're going to have a look at to start with is a seesaw, and a problem I have regularly as someone who goes to parks regularly with my son. So Max, well, this is the seesaw in the first place. This is the pivot of the seesaw. The posh word for it is a fulcrum, I think. It's not one L, it's two L. Sorry, it's one L, not two L's. So it's a fulcrum. And at one end I have Max, and Max weighs 18 kilograms. So the force acting downwards to do with Max is 18G. And let's just say for argument's sake that this length between the fulcrum and Max is 2 meters. Now I'm on the other side, and these are scale drawings. I'm on the other side, and whenever we go to the park, I sit on the other side and I start thinking about moments because I'm a maths geek. And I think, where shall I sit on this side so that Max and I can actually do a seesaw, as opposed to me just sitting right at the end here and him never being able to go up, or me flying him up in the air, or sitting so close to here that actually I can't do anything whatsoever. So there is some point along here which is optimum for me to actually have a bit of a seesaw with Max. Now I weigh roughly 80 kilograms, so my force going downwards is 80G, 80 times gravity. So what we want to do today is decide what this value of x is, and look at how we can apply this situation to lots of different examples. Okay, so we'll come back to that one in a minute, but what we're going to do today is something called moments. So to start with the definition, the moment of a force around a point O is defined by moment equals force times distance from O. And when I say the distance, I specifically mean the perpendicular distance. So, for instance, if I had, let's say, some point O and a light string, let's say the light string comes up this way, and I act on a force on it going up here, and let's call that 6 newtons. It's at a right angle to the string, and let's say that this distance here is 2 meters. Then the moment moments is equal to 6 times 2, which is 12. And notice that moments are force, newtons, times distance, meters, and so the unit for moments is Newton meters. Okay, how about if I did this then? How about if I did something ever so slightly different? So if I did this instead, this is the same length, 2 meters. That's a right angle, and this is 6 newtons. So what would the moment be this time? Well, this is a bit of a, well, some people just say it's another 12 newtons. However, we need to be able to differentiate between these two. This one blatantly goes around this way. This one is going to go clockwise instead. These two things are noticeably different. Both of these have got a force of 6 newtons. So when I'm doing a question, and when you're doing questions too, you guys should be thinking about clockwise or anti-clockwise. The ones that go anti-clockwise are thought of as positive, just like in many other areas of maths, and the ones that go clockwise are thought of as negative moments. The reason for that is essentially if this was just one thing, if I had one piece of string and someone pulled it up that way with 6 newtons, another person pulled it this way with 6 newtons, well, it wouldn't go anywhere because these things are counteracting each other. And we'll look at seeing how the mathematics works with that in a bit, about the idea of something staying in equilibrium, in other words, not moving. So, this moment, yes, it's still 6 times 2, but the way I've always done this is if I put a minus sign between in front of the force in a bracket, just to say to myself, oh yes, this is going to be a negative moment because it's clockwise, and then on my next line I've got negative 12 Newton meters. The reason why I don't put just minus 6 here is because it says 6 in the question, so I'm just sort of, I suppose, artificially timesing this product by minus 1 to get minus 12 Newton meters. But writing the minus in the bracket there signifies to the examiner and makes me sure I don't forget that it's actually going clockwise. A lot of people write things like that, equals moment equals 6 times 2, which equals minus 12, and that just seems wrong on so many different levels. So if you put the minus in brackets, if it's going clockwise, then you'll remember to times it through on the next line, and everything seems to stay quite well together. So just to really quickly practice that one, and I promise I'll actually attach the question sheet this week. Can you just go to exercise 4.1 and can you just do question 1 please really quickly? That won't take you very long. Pause the video and come back to me once you've done that and checked your answers. Okay, so hopefully that went fine. Let's have a look at a slightly more complex example. This example has got 2 forces acting in it. I think on the last example I said strings, and I really shouldn't have said strings, and we need to think about these things as rods or something else which is rigid. So what's happening here is I've got this centre, the rod's coming out of it, and there's a force here which is trying to turn this centre round that way. So imagine it just rotating in the centre. This is doing exactly the opposite, that's trying to rotate it the other way round. So what we want to try and find out with this example is if these 2 forces are acting on these rigid poles coming out of this centre, this spinning top or whatever we want to call it in the middle, which way is this whole system going to go? Is it going to start rotating clockwise or anti-clockwise? So let's find the total moment. So we can write the word moment down again, and let's think about the anti-clockwise ones first because we know they're positive. So I've got 10 times 2, and then I've got the second force. So I'm going to add this second force on. This force is acting in a negative direction, so I'm going to put a minus sign in front of it, and then times by 3, which is the distance. 10 times 2 is 20 newtons, plus negative 7 times 3 gives me negative 21. In other words, minus 1 Newton meter. So this whole system, the resultant, the moment, if I calculate the moments around this centre, the resultant force going round is actually minus 1 Newton meter. So it's actually going to go around this way. It's going to go around clockwise with that force. Okay, so what I'd like you guys to do is go back to exercise 4.1, and can you just have a go at question 2 and then come back to the video. Okay, coming back to the original question we had earlier, we said Max is 2 meters away from the fulcrum. I'm X meters away from it. I weigh 80 kilograms, Max weighs 18. And the question was, basically, is this system going to be in equilibrium? Am I going to be sat at a point where neither I'm dominating this or Max is? It just requires one of us to be able to reach the floor to push off to get the situation going. So I want us to be balanced. I want these forces to be in equilibrium, and if I want these forces to be balanced, basically I want no turning happening around here. If I want no turning happening around here, then the moment generated by me has got to be equal and opposite to the moment generated by Max. So the total moment, in other words, must be 0 if this isn't rotating at all. So if the total moment is 0, and that's equal to the 2 moments that are acting, we've got this one, which is me. I'm going around in the positive direction. So that's the force is 80g times x. Max is happening in the clockwise direction, so he's minus 18g times 2. If I just cancel some bits out, I can cancel g out from everything, because if I divide by g, everywhere that goes. And so I'm left with 80x take away 36. In other words, 80x equals 36, and so x will be 0.45 meters. So if I'm sat 45 centimeters away from the fulcrum, we should be balanced. And then it just need my legs to reach the floor and start us going, and then Max can push, etc., etc., etc. So this is a really good example of a system that has been balanced, and I've specifically said that I'm going to be thinking about moments around this point here. However, it doesn't actually matter if I take moments around here or moments around a different point. If I took moments around a different point, I could still work out how to keep this seesaw still. So if we choose to take moments from a different place instead of from the fulcrum, what we could do is take moments from here, for instance. Let's say this is point A. So at the moment, if I look at point A, I've got 80g and 18g trying to push it this way. Now we know that the seesaw isn't going to start going down that way and go into the earth. So there's obviously something that's also pushing the seesaw back up. And that force is here at the fulcrum. The force at the fulcrum is the total weight of the seesaw. And that's because the seesaw isn't sinking into the ground, it's balancing on top of the fulcrum. If there's 80g and 18g sat on top of what we are assuming to be a seesaw that doesn't weigh anything, then this reaction force here must be 98g. And so if I now take moments around A, I've got 98g going in the anti-clockwise direction. I'm assuming that this thing's going to be in equilibrium, because I said earlier that had to be if I was 1.55 meters along here. So I've got 98g acting in this direction, and that's times by 2. And then I've got this 80g, so I've got minus 80g times 1.55, and then I've also got minus 18g times 4. So hopefully that should equal 0 altogether. I can get rid of the g straight away. 2 lots of 98 is 196. And I've got minus 1.5 times 80 is whatever 1.5 times 80 is. 124. And 18 times 4 is 72. And what have we got here? 196 minus 124 minus 72. So this checks out. They are in equilibrium. Okay, so just one more example. So here's a here's a rod. This rod is 4 meters long. This rod weighs 10 kilograms. This force here, because it's the weight of the rod, is acting in the middle of the rod, so this is 2 meters either side of it. There's also a weight sat on the rod which weighs 20 newtons, and then the rod is held up by 2 strings here. And what we'd like to know is what is the tension in these strings. So there's a couple of ways we can do this. What we're going to, the rod isn't moving, by the way, so it's stationary. So what we're going to do is by taking moments around A. Now it's important to say where you are taking moments around if you are going to do it in different places. So taking moments around A. So taking moments around A, this force here is 0 distance away from A, so this doesn't contribute. However, this force contributes. There'll be a force that comes out of this one, and you should add that to your diagram. That's going to be 20. Notice this is 20 newtons, so it's just a 20, and this is 10 kilograms, so it's 10 G. And then I've also got this force acting upwards. So the total moment is equal to, we've got 10 G acting clockwise, so that's negative 10 G times 2, because it's 2 meters long. Then we've got this minus 20 acting down as well. This is 1 meter, so I should have stuck that in. It's 1 meter. So this is 3 meters from A. And then I've got this tension here, which is acting upwards. And this is 4 meters from the start, so that's T times 4. Now I know this isn't going up or down. We're going to say this is an equilibrium. So if it's an equilibrium, then the total moment must be equal to 0. So that's going to be 2 times minus 10G. In fact, actually, let's just get this G out because it's just going to make things harder. So imagine that the G was never there. Imagine this is just a 10 Newton weight. So I've got minus 20 newtons from this bit. I've got minus 20 times 3, so that's minus 60. And then I've got also 4 lots of T. So that must mean that 4T is equal to 80. And so T is just equal to 20 newtons. So now to find force F, and I'm a little bit annoyed about the numbers I picked now. So we know this is 20 newtons going up, this is 20 newtons down, this is 10 newtons down, and we want to find out what F is now. So we could take moments again, we could take moments around B, for instance, to find out what F is, but there's actually a much simpler and quicker way to do this. So we know that the total weight of the bar going downwards is 10 plus 20. So essentially we're resolving vertically. Say resolving vertically. So I'm just drawing an arrow to specify up. Resolving means I'm just trying to compare the forces with each other. So because there's 30 newtons acting downwards altogether, and this rod is not moving up or down, then that 30 newtons better be equal to T plus F, because there's no other forces acting on this thing, and it is stationary. So that must mean that 30 newtons is equal to, well, we found it earlier that T was 20, and so therefore F must be 10 newtons. Okay, what I'd like you guys to do now is have a go at exercise 4.1, and can you do questions 3, or which other ones did I write down to do? 4, 5 and 8. Once you've had to get those, can you mark those? And otherwise, that's enough for today, and I will see you guys tomorrow. Thanks very much. Bye-bye.